In computing, a compiler is a computer program that translates computer code written in one programming language or the source language into another language or the target language. The name compiler is primarily used for programs that translate source code from a high-level programming language to a low-level programming language to create an executable program. There are many different types of compilers which produce output in different useful forms. A cross-compiler produces code for a different CPU or operating system than the one on which the cross-compiler itself runs. A bootstrap compiler is often a temporary compiler used for compiling a more permanent or better optimized compiler for a language. A compiler is likely to perform some or all of the following operations, often called phases: preprocessing, lexical analysis, parsing, semantic analysis, syntax-directed translation, conversion of input programs to an intermediate representation, code optimization, and machine-specific code generation. Compilers generally implement these phases as modular components, promoting efficient design and correctness of transformations of source input to target output. Program faults caused by incorrect compiler behavior can be very difficult to track down and work around. Therefore, compiler implementers invest significant effort to ensure compilers are not the only language processors used to transform source programs. An interpreter is computer software that transforms and then executes the indicated operations. P2. The translation process influences the design of computer languages, which leads to a preference for compilation or interpretation. Theoretically, a programming language can have both a compiler and an interpreter. In practice, programming languages tend to be associated with just one. Theoretical computing concepts developed by scientists, mathematicians, and engineers formed the basis of digital modern computing development during World War II. Primitive binary languages evolved because digital devices only understand ones and zeros and the circuit patterns in the underlying machine architecture. In the late 1940s, assembly languages were created to offer a more workable abstraction of the computer architectures. Limited memory capacity of early computers led to substantial technical challenges when the first compilers were designed. Therefore, the compilation process needed to be divided into several small programs. The front-end programs produce the analysis products used by the back-end programs to generate target code. As computer technology provided more resources, compiler designs could align better with the compilation process. Between 1942 and 1945, Konrad Zuse designed the first algorithmic programming language for computers called Planck-Alcal, Plan Calculus. Zuse also envisioned a plan assembly device to automatically translate the mathematical formulation of a program into machine-readable punched film stock. While no actual implementation occurred until the 1970s, it presented concepts later seen in APL, designed by Ken Iverson in the late 1950s. APL is a language for mathematical computations. Between 1949 and 1951, Heinz Rudeshauser proposed Superplan, a high-level language and automatic translator. His ideas were later refined by Friedrich L. Bauer and Klaus Samuelson. High-level language design during the formative years of digital computing provided useful programming tools for a variety of applications. Fortran, formula translation, for engineering and science applications, is considered to be one of the first actually implemented high-level languages and first optimizing compiler. COBOL, Common Business-Oriented Language, evolved from A0 and Flow-Matic to become the dominant high-level language for business applications. Lisp, list processor, for symbolic computation. Early operating systems and software were written in assembly language. In the 1960s and early 1970s, the use of high-level languages for system programming was still controversial due to resource limitations. However, several research and industry efforts began the shift toward high-level systems programming languages. For example, BCPL, Bliss, B, and C. Bell Labs left the Multics project in 1969 and developed a system programming language B based on BCPL concepts, written by Dennis Ritchie and Ken Thompson. Ritchie created a bootstrapping compiler for B and wrote an Unix operating system for a PDP-7 in B. Unix eventually became spelled Unix. Bell Labs started the development and expansion of C based on B and BCPL. The BCPL compiler had been transported to Multics by Bell Labs, and BCPL was a preferred language at Bell Labs. Initially, a front-end program to Bell Labs B compiler was used while a C compiler was developed. In 1971, a new PDP-11 provided the resource to define extensions to B and rewrite the compiler. By 1973 the design of C language was essentially complete, and the Unix kernel for a PDP-11 was rewritten in C. Steve Johnson started development of Portable C Compiler (PCC) to support retargeting of C compilers to new machines. Object-oriented programming (OOP) offered some interesting possibilities for application development and maintenance. OOP concepts go further back, but were part of Lisp and Simula language science. Bell Labs became interested in OOP with the development of C++. C++ was first used in 1980 for systems programming. The initial design leveraged C language systems programming capabilities with Simula concepts. Object-oriented facilities were added in 1983. The Cron program implemented a C++ front-end for C84 language compiler. In subsequent years several C++ compilers were developed as C++ popularity grew. High-level languages continued to drive compiler research and development. Focus areas included optimization and automatic code generation. The advent of web services promoted growth of web languages and scripting languages. Scripts trace back to the early days of command line interfaces, CLI, where the user could enter commands to be executed by the system. User shell concepts developed with languages to write shell programs. Early Windows designs offered a simple batch programming capability. The conventional transformation of these language used an interpreter. While not widely used, Bash and Batch compilers have been written. More recently sophisticated interpreted languages became part of the developer's toolkit. Modern scripting languages include PHP, Python, Ruby and Lua. Lua is widely used in game development. Now I will talk about some C++ compilers and when you should use them for your work. Compiler Collection is an optimizing compiler that supports a variety of programming languages, hardware architectures, and operating systems produced by the GNU project. The Free Software Foundation, FSF, distributes GCC as free software under the GNU General Public License, GNU GPL. GCC is a core component of the GNU toolchain and the standard compiler for most projects related to the GNU and Linux kernels. With roughly 15 million lines of code in 2019, GCC is one of the largest free programs in existence. It has played an important role in the growth of free software, both as a tool and as an example. You can use this for all projects. Second choice is the Clang compiler. Clang is a compiler front-end for the C, C++, Objective-C, and Objective-C++ programming languages, as well as the Open, OpenCL, RenderScript, CUDA, SYCL, and HIP frameworks. It acts as a drop-in replacement for the GNU Compiler Collection, GCC, supporting most of its compilation flags and unofficial language extensions. It includes a static analyzer and several code analysis tools. Clang operates in tandem with the LLVM compiler backend and has been a sub-project of LLVM 2.6 and later. As with LLVM, it is free and open-source software under the Apache License 2.0 software license. Its contributors include Apple, Microsoft, Google, ARM, Sony, Intel, and AMD. Clang 17, the latest major version of Clang as of October 2023, has full support for all published C++ standards up to C++ 17, implements most features of C++ 20, and has initial support for the upcoming C++ 23 standard. Since v16, Clang compiles C++ using the GNU++ 17 dialect by default, which includes features from the C++ 17 standard and conforming GNU extensions. Can use this for all projects. Third choice is the Visual C++ compiler. Microsoft Visual C++, MSVC, is a compiler for the C, C++, C++, CLI and C++ CX programming languages by Microsoft. MSVC is proprietary software. It was originally a standalone product, but later became a part of Visual Studio and made available in both trialware and freeware forms. It features tools for developing and debugging C++ code, especially code written for the Windows API, DirectX and .NET. Many applications require redistributable Visual C++ runtime library packages to function correctly. These packages are frequently installed separately from the applications they support, enabling multiple applications to use the package with only a single installation. These Visual C++ redistributable and runtime packages are mostly installed for standard libraries that many applications use. Fourth choice is the Intel C++ compiler. Intel C++ compiler Classic, or Intel's C, C++, SYCL, and Data Parallel C++, DPC++, compilers for Intel processor-based systems, available for Windows, Linux, and Mac OS operating systems, as well as GPUs, including Intel Processor Graphics GEN9 and above, Intel Z architecture, and Intel Programmable Acceleration Card with Intel Area 10GX FPGA. Like Intel C++ Compiler Classic, it also supports the Microsoft Visual Studio and Eclipse IDE development environments and supports threading via Intel and EP threading building blocks, OpenMP, and native threads. DPC++ builds on the SYCL specification from the Khronos Group. It is designed to allow developers to reuse code across hardware targets and perform custom tuning for a specific accelerator. DPC++ comprises C++17 and SYCL language features and incorporates open-source community extensions that make SYCL easier to use. Many of these extensions were adopted by the SYCL 2020 provisional specification, including unified shared memory, group algorithms, and subgroups. Intel announced in August 2021 the complete adoption of LLVM for faster build times and benefits from supporting the latest C++ standards. IT supports the Microsoft Visual Studio and Eclipse IDE development environments. Intel C++ Compiler Classic supports threading via Intel and EP threading building blocks, OpenMP, and native threads. If the program you're writing only works with specific compilers, you're probably doing the wrong thing or can work a little on making it more portable. You get to a point where compiler choice makes a significant performance impact for you, then you've already perfected everything else in your program, and you're in a good state, and you are also quite advanced in your abilities. If you use a Unix-based machine, Linux, Mac, actual Linux, then pretty much GNU G++ is the way to go and is fairly much standard. If it's good enough to compile your OS, it's probably good enough for you. On a Mac you can use Xcode as your IDE, and it interfaces well with G++. On Linux some people prefer command line tools, though you might like the Eclipse C++ support, it is much better today than it was 3 to 4 years ago. Things on Windows are trickier. If you can afford it, have access to, or are eligible for one of the free editions, I think the Microsoft Visual C++ environments are pretty good for learning, and they are used in production. I think there's actually a lightweight Visual Studio now with an emphasis on C++ that could be a good start.